Okay, in this podcast, we're going to talk about how to write the law of mass action, also known as the equilibrium constant expression. And more often on the AP test, I've seen it expressed as the equilibrium constant expression, but in college, you're likely to see it as the law of mass action. Okay, so the equilibrium constant expression is based on a balanced chemical equation, so stoich does matter. And one of the nice things about equilibrium constant is it has no units, so we don't have to worry about what the units are. And that's because units will cancel. So if I have an equation where I have coefficient A for reactant A, coefficient B for reactant B, producing products C and D with their respective coefficient, then the equilibrium expression is simply the products, concentration of the products over the concentration of the reactants. And as you know, this symbol means concentration or molarity. Okay. Now it's not quite as simple as that because it's not just products over reactants, but the concentration of each product needs to be raised to its stoichiometric coefficient, and the same thing with the reactants. Okay, but not too hard to do. So here, let's take a look at this example. So here we have H2 plus O2 becoming H2O2 in the gaseous state. So I take my products, which is H2O, raise it to its coefficient, which is 2, and I put that over my reactants, and I have H2 raised to the 2, which is the coefficient, times the concentration of O2. And again, these brackets mean concentration. So if we're talking about molarity or concentration, we need brackets. If we're talking about things like pressure, which we will be soon, you don't want to use brackets because brackets mean concentration. Okay. One of the other nice things about equilibrium constants is the expressions do not include the solids. We omit the solids because their concentration is constant. So if you think about it, if I am changing how much of let's say, ammonium chloride I have in this reaction flask, at the same time I'm adding more moles of ammonium chloride, I'm also adding more volume, right? More liters of it. So they change in a proportional way to each other, so we can leave them out of the expression. Okay, so in the case of this equation, we would just say Kc is the concentration of the products times N2, and they are not over anything because the ammonium chloride is solid, so it's just going to be 1, so it would be over 1. So I can just show it as the products. Okay, so here's another one. We have carbon monoxide becoming carbon dioxide and carbon. Because carbon is a solid, I eliminate it from the balanced or from the equilibrium calculation. So it's just simply the gaseous CO2. It's got a coefficient of 1, so there's no power there, over the concentration of carbon monoxide raised to the 2. Now I have this term K, I've added a C here, and that means equilibrium constant for concentration, C for concentration, or molarity. And that's what, again, these boxes mean. And we're going to distinguish that from Kp and eventually from things like Ka and Kb and Ksp. Sounds like fun, right? We're going to learn all about different Ks. But the Kc refers to concentration. And generally when you see K without a C or an A or a B or a P, it usually can assume it's Kc. Okay. Other piece of good news that goes along with solids being excluded are that pure liquids are also excluded for the same reason. Now we can also think about why we can eliminate water. So water, for instance, if I were to look at the molarity of water, it's going to be moles of water per liter of solution, right? So if I have 1 liter, that's 1,000 milliliters, right? And because the density of water is 1 gram per milliliter, this would be 1,000 grams. And if I divide that 1,000 grams of water by the molar mass of water, 18.02 grams per mole, I get some ridiculously high molarity, like 55.5 molar. Really going to be tough to change that compared to anything else that you can do. So liquids, including water, are also eliminated from the equilibrium expression. So let me just clear out some of this garbage. And so here is my expression. I just use oxygen over hydrogen peroxide raised to its coefficient. All right, so what does K tell us? So because K is a ratio of products over reactants, the magnitude of K can tell us a lot. First of all, if K is equal to 1, my products over my reactants is a ratio of 1, which means I am at equilibrium. Okay? Now, if K is much greater than 1, then the products over the reactants are greater than 1. That means I have a lot more products, right? If K is much greater than 1, I'm going to have a lot more products. So products would be favored. If my K likewise is much less than 1, that would mean that I'm going to end up with far more reactants than I do products. Okay? So K's can tell me something about whether my reaction is product or reactant favored. Which way is it most likely to go? And it's not going to go totally any one way, but it's which one is favored. Okay, so let's see if you can figure out what the law of mass action is for the reaction A to B. Also, this is the equilibrium constant expression. So take a second and do that. Okay, so I'm hoping you picked B because B is my product. It goes over A. Coefficients are 1, so that's all I need. Okay, so try writing the law of mass action or the equilibrium expression for all of these. And I would pause and then come back when you're done. So I'm just going to do A. So A is going to be, I first look at it and see if there's any liquids or solids. Now aqueous doesn't mean liquid, right? It means something that's dissolved. So for A, it's going to be C, concentration of C, over A, concentration of A, and the concentration of B, right? So my K is equal. In all cases, K is equal to. In the case of B, my D is a solid. So my K is my product, and I'm just going to put a 1 there, over A squared. For C, these are all aqueous, so it's going to be K is equal to C squared over A and B concentrations, right? And my D, I have a liquid here, so it's just going to be concentration of C over the concentration of A is equal to K. And then we have one more E. I'll squeeze it down here. Here I have solid B, solid A, so my K is simply the concentration of C. Okay, so that's going to do it. We're going to stop there.